On November 2001, the Parkes Radio Telescope in Australia detected something that shouldn't exist. A radio signal, incredibly bright, lasting just 5 milliseconds, coming from a direction billions of light years away. The signal released as much energy in 5 milliseconds as the sun emits in a month, packed into radio wavelengths from a source smaller than Earth. Then it vanished, completely, never to repeat. The discovery sat in archived data for 6 years before graduate student David Narkovic noticed it while analyzing recordings. By then, the source was long gone, if it had ever been there at all. Astronomers called it the Lorimer Burst, after Duncan Lorimer, who led the team. It was the first fast radio burst ever detected. For years, it remained alone, an anomaly, possibly instrumental error, terrestrial interference, or cosmic fluke. Then we found another, and hundreds more. Today, we detect fast radio bursts, FRBs, almost daily, over 800 catalogued from all across the sky. Most appear once and disappear forever. Some repeat unpredictably. One repeats with clockwork precision every 16 days. We don't know what creates them. Theories range from magnetars to alien signals to cosmic strings to physics we haven't discovered yet. What we know, FRBs are real. They're scattered throughout the universe. They carry information about the cosmic web, intergalactic space, and extreme physics. They represent one of the greatest mysteries in modern astronomy, signals of immense power, microseconds in duration, arriving from the deepest reaches of space. And we're only beginning to understand what they might be telling us. If you enjoy this documentary, hit the like button and subscribe for more cosmic mysteries. In 2007, Duncan Lorimer and his team published a paper titled "A Bright Millisecond Radio Burst of Extragalactic Origin." The signal, later designated FRB 010724, had been recorded on July 24, 2001 by the Parkes 64-meter radio telescope during a survey of the Magellanic Clouds. Characteristics: duration, 5 milliseconds, dispersion measure, 375 parsecs per cubic centimeter, peak flux density, 30 Janskis, inferred distance, approximately 1 billion light-years. The dispersion measure, DM, was crucial. Radio waves traveling through plasma experience dispersion. Higher frequencies arrive slightly before lower frequencies. The amount of dispersion indicates how much ionized material the signal passed through. A DM of 375 far exceeded what the Milky Way's electrons could produce. The signal had traveled through intergalactic space, picking up dispersion from the cosmic web's diffuse plasma. This meant an extragalactic origin. Something billions of light-years away had produced a radio burst detectable across the universe. The implied energy was staggering. To be visible at that distance, the source had released about 10 to the 33rd joules in milliseconds, roughly the sun's total energy output for an entire month, concentrated into a flash shorter than a heartbeat. Not everyone believed it. The signal could have been terrestrial interference, a satellite, radar, even a microwave oven. Radio telescopes are exquisitely sensitive. They detect cosmic whispers, but also earthly shouts. Or perhaps instrumental glitches. Electronics can produce spurious signals mimicking astrophysical sources. Or astronomical, but local. A pulsar glitch, a solar flare, something in our galaxy misidentified as distant. The Lorimer Burst's team performed checks. No corresponding optical, X-ray, or gamma-ray events, no known pulsars or transients at that position, no terrestrial sources could explain the dispersion measure. The signal's properties matched theoretical predictions for extragalactic transients. But one event proves nothing. Anomalies happen. Astronomers searched for more. Surveys combed archival data. New observations scanned the sky. Years passed. Nothing. Then, in 2012, the Arecibo telescope in Puerto Rico detected 4 more FRBs. Different positions, different dispersion measures, but similar characteristics: millisecond duration, extragalactic distances, enormous energies. FRBs were real. In 2012, the Arecibo telescope detected FRB 121102. Initially, it seemed like others, a single bright burst from a distant galaxy, never to repeat. But in 2015, it did repeat. Multiple bursts from the same sky position, different intensities, irregular timing, but unquestionably from the same source. This changed everything. Repeating FRBs can be studied. Astronomers can point multiple telescopes at the source, waiting for the next burst. They can observe across wavelengths: radio, optical, X-ray, searching for counterparts. In 2017, the Very Large Array in New Mexico and the Gemini North Telescope in Hawaii pinpointed FRB 121102's location, a dwarf galaxy 3 billion light-years away. Even more remarkably, the FRB originated from a persistent radio source, something continuously emitting faint radio waves. This source coincided with a region of intense star formation. Follow-up observations revealed the bursts were highly polarized, suggesting strong magnetic fields. Rotation measures indicated magnetic fields exceeding anything in normal astrophysical environments, except magnetars. The host galaxy was metal-poor and actively forming stars. The pieces suggested magnetars, neutron stars with magnetic fields 1,000 times stronger than typical pulsars. But this was speculation. Correlation isn't causation. In 2017, CHIME, the Canadian Hydrogen Intensity Mapping Experiment, came online in British Columbia. CHIME is unlike traditional radio telescopes. No moving dish, instead 4 100-meter-long cylindrical reflectors lined with 1,024 dual polarization antennas scanning the sky as Earth rotates. CHIME was built to map hydrogen in the universe, studying cosmic expansion and dark energy. But its wide field of view and sensitivity made it perfect for detecting FRBs. Within months, CHIME started finding FRBs. Dozens, then hundreds. By 2024, CHIME had detected over 500 FRBs. The catalog revealed patterns. Most FRBs don't repeat. They appear once and vanish, suggesting cataclysmic one-time events. Some FRBs repeat. About 3% show multiple bursts. These repeaters tend to have different properties than one-offs: lower frequencies, wider pulse shapes, more scattering. FRBs come from all distances. Some originate in our cosmic neighborhood, tens of millions of light-years. Others come from near the edge of the observable universe, billions of light-years. FRBs favor certain environments. Many repeaters occur in star-forming regions. One-off FRBs show no clear environmental preference. At least one FRB repeats periodically. FRB 180916 repeats with a 16.35-day cycle, active for about 4 days, then silent for about 12 days, like clockwork. The flood of detections transformed FRBs from curiosities into a field of study. On April 28, 2020, multiple radio telescopes detected a powerful radio burst from within the Milky Way. The source? SGR 1935 plus 2154, a known magnetar about 30,000 light-years away. The burst lasted milliseconds, showed similar structure to extragalactic FRBs, and coincided with an X-ray burst from the same magnetar. This was the smoking gun linking FRBs to magnetars. If SGR 1935 plus 2154 had been in a distant galaxy, we'd classify it as an FRB based on its radio properties. But because it was local, we could observe it across wavelengths and confirm the source. Key observations. Radioluminosity matched the faintest extragalactic FRBs. X-ray burst showed magnetar activity, crustal fracture or magnetic reconnection. Polarization consistent with emission from extreme magnetic fields. No optical counterpart. This single event confirmed what many suspected: at least some FRBs come from magnetars. But does this explain all FRBs? Probably not. One-off FRBs might have different origins than repeaters. FRB dispersion measures map the universe's ionized content. Radio waves traveling through ionized plasma slow down slightly, with lower frequencies delayed more than higher frequencies. The dispersion measure quantifies this. dm equals integral NE/dL, where NE is electron density and the integral is along the line of sight. FRBs from cosmological distances accumulate dispersion from the Milky Way's interstellar medium, the FRB host galaxy, and intergalactic space along the path. By measuring dm and subtracting Milky Way contributions, astronomers probe the intergalactic medium, the diffuse plasma in cosmic voids and filaments. This tests cosmological models. The universe's baryon density, normal matter, is well constrained by Big Bang nucleosynthesis and the cosmic microwave background, but much of this matter is missing, not in stars or detectable gas. FRBs might reveal where it's hiding. Recent studies using FRB dispersion measures suggest 80% of baryons reside in the intergalactic medium, exactly as predicted. FRBs are detecting the cosmic web's tendrils. Precise localizations reveal FRB diversity. Over 50 FRBs have been localized to specific host galaxies. These show diverse galaxy types, spiral galaxies, ellipticals, dwarfs, massive galaxies, low-mass galaxies. No single environment dominates. Various star formation rates. Some hosts are actively forming stars. Others are quiescent, with star formation ceased billions of years ago. Wide redshift range from Z equals 0.03, nearby, to Z equals 1.4, 8 billion light-years away. This diversity suggests multiple progenitor types. Perhaps magnetars explain repeaters in star-forming galaxies, while other mechanisms, neutron-star mergers or collapsing supramassive neutron stars, explain one-off FRBs in quiescent galaxies. FRB 180916 exhibits a 16.35-day activity cycle. For about 4 days, it emits bursts irregularly, sometimes many per day, sometimes none. Then it goes silent for about 12 days. This pattern repeats with remarkable regularity. Possible explanations: binary system. The FRB source orbits a companion star or black hole. Geometric effects, beaming, or environmental interactions, wind, modulate burst visibility. Precession. The Magnetar's rotation axis precesses with a 16-day period, sweeping the emission beam in and out of our line of sight. Tidal interactions. A companion's tidal forces stress the Magnetar's crust periodically, triggering bursts at specific orbital phases. Observations constrain models. Bursts occur preferentially at lower radio frequencies during the active window. No optical or X-ray counterpart detected during bursts. Activity window is remarkably consistent over multiple cycles. A second periodic repeater, FRB 121102, may have a 157-day cycle, though this is less certain. Periodicity provides a tool for understanding FRB environments and mechanisms. Some FRB bursts show extreme Faraday rotation. Linearly polarized radio waves rotating as they pass through magnetized plasma undergo Faraday rotation. The polarization angle rotates. The amount depends on magnetic field strength and electron density. FRB 121102's bursts showed rotation measures exceeding 100,000 radians per meter squared, among the highest ever measured for any astrophysical source. This implies the FRB originates in or near an environment with extreme magnetic fields. Dense plasma surrounds the source. The combination suggests magnetars in supernova remnants or near massive stars. Rotation measures vary over time for repeating FRBs, indicating the local environment evolves. Perhaps the magnetar is moving through a changing medium, or the medium itself is dynamic. FRBs release extraordinary energy in milliseconds. Consider FRB 121102's brightest bursts, luminosity around 10 to the 43rd ergs per second during the burst. That's 100 times the sun's total luminosity, concentrated into milliseconds and radio wavelengths. Where does this energy come from? Magnetar model, magnetic field energy. Magnetar fields contain roughly 10 to the 47 ergs. Sudden magnetic reconnection or crustal fractures could release roughly 10 to the 40 ergs per event, enough for an FRB. But this requires efficient conversion of magnetic energy to coherent radio emission. The mechanism remains unclear. Alternative models, pulsar-powered, a young, rapidly spinning neutron star dumps rotational energy into surroundings, powering radio bursts. Supramassive neutron stars above the normal mass limit, supported temporarily by rapid rotation, collapse and produce FRBs. Black hole evaporation. Primordial black holes evaporating in final moments, very speculative. Cosmic strings, colliding or oscillating cosmic strings, extremely speculative. Most evidence favors magnetars for repeaters. One-off FRBs might involve different physics. Some FRBs show a frequency drift. Higher frequencies arrive before lower frequencies beyond what dispersion alone predicts. This sad trombone effect suggests emission occurs over a range of altitudes above the neutron star surface. Higher frequencies originate closer to the star, where plasma is denser. Lower frequencies originate farther out, where plasma is thinner. As the emission region expands or the emitting plasma moves, frequency decreases over time. This provides clues about emission mechanisms: plasma outflows or shocks propagating outward, coherent emission from different plasma densities. Analogies with solar radio bursts, but vastly more energetic. The effect also helps distinguish FRB types. Not all show it, suggesting diverse emission physics even within the FRB population. We detect about 1 FRB per day across the entire sky with current instruments. Scaling to the full sky and accounting for detection thresholds suggests about 10,000 FRBs occur per day above detectable levels. Extrapolating to all distances and luminosities, millions of FRBs per day across the observable universe. If FRBs come from magnetars, this implies either magnetars are incredibly common, or each magnetar produces many FRBs over its lifetime, or FRBs come from magnetar subpopulations, young magnetars, specifically magnetized magnetars. But magnetar birth rates, inferred from supernovae, don't obviously match FRB rates unless each magnetar produces thousands of bursts. If FRBs come from cataclysmic events, neutron star collisions, magnetar formation, rates must be much higher than previously thought. The numbers don't quite add up. Something is missing in our understanding. Magnetars, neutron stars with magnetic fields exceeding 10 to the 14 Gauss, are the leading FRB candidates. Their magnetic fields are so strong that quantum electrodynamics effects become important. The vacuum itself polarizes. Atoms would be stretched into needles. FRB emission from magnetars might involve 1. Crustal fractures. The magnetar's solid crust cracks under magnetic stress. Sudden shifts release magnetic energy, accelerating particles and generating coherent radio emission via processes like synchrotron maser emission, plasma bunching and coherent curvature radiation, and relativistic shock acceleration. 2. Magnetic reconnection. Magnetic field lines reconfigure, releasing stored energy. In Earth's magnetosphere, this causes auroras. On magnetars, it's billion times more energetic. 3. Magnetospheric disturbances. The magnetar's magnetosphere, the region dominated by its magnetic field, becomes unstable. Plasma oscillations or wave modes produce coherent radio bursts. The April 2020 galactic magnetar FRB supports these mechanisms but doesn't prove details. Not all magnetars are detected producing FRBs. Why? Possible reasons. Beaming. FRB emission might be highly directional. We only detect FRBs when the beam points toward Earth. Most magnetar FRBs miss us. Evolutionary phase. Perhaps only young magnetars, first 10,000 years, or very old ones, after millions of years, produce FRBs. Intermediate age magnetars might be radio quiet. Magnetic field geometry. Specific field configurations might be necessary. Not all magnetars have the right setup. Environmental factors. Dense plasma or companion objects might be required to trigger or amplify FRB emission. This explains why FRBs are relatively rare, despite magnetars being more common. While magnetars are favored, alternatives exist. Collapsing supermassive neutron stars. Neutron stars slightly above the mass limit can be temporarily supported by rapid rotation. When rotation slows, they collapse to black holes. The collapse might produce an FRB. Neutron star mergers. Binary neutron stars spiraling together might produce FRBs just before merging. The 2017 gravitational wave detection, GW170817, from merging neutron stars showed no FRB, but perhaps only certain mergers produce them. Black hole neutron star interactions. A neutron star orbiting a black hole experiences tidal forces. If torn apart, the disruption might generate FRBs. Exotic physics. Cosmic strings, hypothetical topological defects from early universe, axion stars, condensates of dark matter, or other beyond standard model physics. Most exotic models lack supporting evidence. They're speculative, but not ruled out. Current facilities detect hundreds of FRBs annually. Next-generation instruments will detect thousands. CHIME upgrades, improving sensitivity and adding outrigger stations for better localization. Meerkat, South Africa, 64-dish array already detecting FRBs. Upgrades will increase rates. ASCAP, Australia, Australian Square Kilometre Array Pathfinder, designed for wide field surveys. SKA, Square Kilometre Array, when complete, 2030, SKA will detect thousands of FRBs daily. Its sensitivity will probe faint FRBs, distant FRBs, and frequency structures in detail. Deep Space Network, NASA's DSN, used for spacecraft communication, can detect extremely bright FRBs. With large samples, astronomers will classify FRBs into populations with distinct properties, map FRB host environments comprehensively, use FRBs to probe the cosmic web and intergalactic medium, test whether FRB properties evolve with cosmic time, redshift. FRBs aren't just interesting in themselves, they're tools. Mapping the cosmic web, FRB dispersion measures trace ionized gas. Combined with redshifts, they map baryonic matter distribution across cosmic scales, probing the universe's large-scale structure. Constraining dark energy, if FRBs have standard properties, standard candles or rulers, they could measure cosmic expansion history, complementing supernova and CMB observations. Detecting intervening structures, if an FRB passes through a galaxy cluster or filament, dispersion and scattering reveal the intervening structure's properties. Probing magnetic fields, Faraday rotation from FRBs maps magnetic fields in galaxies, clusters, and intergalactic space, regions where field strengths are otherwise unmeasurable. Testing fundamental physics. Precise arrival times test dispersion in vacuum, probing quantum gravity effects, while polarization tests relativity in strong fields. FRBs transform from mystery to tool. Could FRBs be artificial? When FRBs were first discovered, some considered this possibility. Extremely powerful radio signals from deep space, perhaps alien beacons or propulsion systems? Arguments against. Energy requirements. FRB luminosities exceed what any plausible civilization could generate. Even Kardashev Type II civilizations, harnessing a star's entire output, would struggle. Occurrence rate. Thousands per day suggests either absurdly many civilizations or natural phenomena. Host environments. FRBs occur in extreme environments, star-forming regions, magnetar vicinity, incompatible with life. Physical mechanisms. FRB properties match natural astrophysical models, magnetars, neutron stars, no need for artificial explanations. The SETI hypothesis is essentially ruled out for FRBs. But the question highlights an important point. If we detected genuinely artificial signals, we'd need to distinguish them from natural transients. FRB studies inform how we'd recognize technosignatures. Recent breakthroughs in real-time FRB detection allow immediate multi-wavelength follow-up, improving localization and classification. Machine learning algorithms now identify FRBs in data streams milliseconds after detection, enabling rapid alert systems. Despite progress, fundamental questions remain. 1. Are all FRBs the same phenomenon? Repeaters and one-offs might have different origins. Even within repeaters, diversity suggests multiple mechanisms. 2. What is the exact emission mechanism? We know magnetars are involved, at least for some FRBs, but how does magnetic energy convert to coherent radio bursts? The microphysics remains unclear. 3. Why the millisecond timescale? This constrains source sizes to approximately 300 kilometers, light travel distance in 1 millisecond, roughly a neutron star. But why that timescale specifically? 4. Why the energy distribution? FRBs span a huge luminosity range. Do faint and bright FRBs share the same physics, or are they distinct? And 5. What determines repetition? Why do some sources repeat while others don't? Is it environmental or intrinsic to the source? Current surveys are biased. We detect FRBs primarily at gigahertz frequencies, 1 to 2 gigahertz, but FRBs might occur at much lower or higher frequencies, invisible to current instruments. We detect FRBs mostly within a few billion light-years. More distant FRBs might be too faint or too dispersed to recognize. We detect bright FRBs. Faint FRBs vastly outnumber bright ones if FRB luminosity functions resemble other transients. The universe might be flooded with faint FRBs we're blind to. If we're missing most FRBs, our understanding of their rates, populations, and origins could be skewed. Future instruments with broader frequency coverage, higher sensitivity, and global sky coverage will reveal the hidden FRB population. FRBs remind us how much we don't know. 20 years ago, FRBs were unknown. Today, they're a major research field. What else are we missing? The universe produces phenomena we haven't imagined. Every advance in observational capability reveals new transients, new signals, new mysteries. FRBs also illustrate how the universe communicates across cosmic distances. These signals travel billions of light-years, carrying information about distant environments, intervening matter, and extreme physics. In a sense, FRBs are messages, not from aliens, but from the universe itself. They encode data about magnetic fields, plasma, space-time, and matter under conditions we can't replicate. Decoding these messages advances our understanding of physics, cosmology, and the nature of reality. FRBs are mysteries, but they're also opportunities, windows into regimes of physics we couldn't otherwise access. We began with a 5 millisecond signal detected in 2001 and published in 2007. Today, over 800 FRBs populate catalogs. We detect them daily. We've localized dozens to host galaxies. We've identified one source, a magnetar, in our own galaxy. FRBs are real. They're extragalactic, they're energetic, and we're beginning to understand them. The evidence points to magnetars as the primary source for repeating FRBs. Magnetic field energy, released through crustal fractures or reconnection, produces coherent radio bursts visible across billions of light-years. One-off FRBs might come from similar processes or entirely different mechanisms, collapsing neutron stars, mergers, or physics we haven't considered. Hundreds of FRBs remain unlocalized. Thousands more will be discovered. Each adds data to constrain models. Future instruments will detect FRBs by the thousands, transforming them from curiosities into tools for probing the cosmos, mapping baryonic matter, testing cosmology, studying extreme physics. The questions outnumber the answers. We don't fully understand emission mechanisms. We don't know if all FRBs share common origins. We don't know what determines repetition rates. But we're learning rapidly. Every FRB detection refines our understanding. Every localized FRB adds context. FRBs went from one mysterious signal to a field of study in just 20 years. In another 20, they might be routine probes of the universe, as familiar as pulsars or quasars. Or they might reveal something entirely unexpected, new physics, unforeseen phenomena, deeper mysteries. The universe speaks in millisecond flashes from across cosmic distances. We're learning to listen, and the signals continue arriving, carrying secrets from the void.